All right, so another thing that we're going to look at here, again, dealing with alcohols, um, is a type of group called a tosylate. And this is something that we can take an alcohol and make a good leaving group out of it. Because if you look at previous reactions, all of these, we were reacting with an alcohol and doing a substitution, we were always getting an alkyl halide as a result. We were using a halogen as a nucleophile. But what if we wanted to use other nucleophiles? So one way to get that versatility is to convert the alcohol into something that's known as a tosylate. So how do we accomplish this? Well, let's start with an alcohol here. I'm going to use a reactant known as para-toluene. We use the letter P to abbreviate para, but p-toluene sulfonyl chloride. And here's the structure. So I would memorize this name and structure, and I'll make it a little bit easier. If you wanted to use its acronym, TSCL, instead of drawing the whole name or instead of drawing the whole structure, you're more than welcome to do that. So you could instead replace this with TSCL, and that's fine. Actually, it should be a lowercase s. Now, this is also done with pyridine. We've seen pyridine before, so make sure you know that. But what this is going to do is the OH, this whole alcohol or this whole thing is going to replace the chlorine. And you get this initially. Now, notice I didn't draw out the whole tosylate group. I just used that abbreviation TS. You are more than welcome to do that. What does TS represent? It represents all of this. So the OH or the whole alcohol replaces the chlorine, and then the pyridine comes in and acts as a base. Just going to use like B for base, pulls off that hydrogen, and this makes what is known as a tosylate. Tosylates are very good leaving groups. Well, why is that? So this whole thing, when this leaves, you get this anion. Now, what would make that a stable leaving group? Well, there's a lot of resonance that you can do for that. I'm not going to draw it all, but it's resonance stabilized. And what this allows us to do is we can now replace that OTS group with a lot of different nucleophiles. We're not limited to just using halides. We can use a lot of other nucleophiles like CN minus or OR minus or OH minus. We could use other nucleophiles that don't have to be halides. And so if we react this with a good nucleophile to go through an SN2, we'll get that as a result. Or what if we wanted to do an elimination? So like, for example, E2 by using a bulky base. Let's just put DBU here. We could get the Huffman elimination. Or if we wanted to get the Zysteff elimination, so again, another E2 here, we could use a strong base with heat. And so you can see there's a lot of different pathways that can result from using a tosylate. And this is going to transition well into the final video of this unit, where we're going to be looking at synthesis, where we're starting with a small compound and doing a whole lot of different things to it. We're not just looking at one reaction, because you'll notice here, we're kind of chaining a lot of reactions. Um, like this is our first reaction here, and then, we're starting with the second reaction here, or doing an elimination. And so this is laying the foundation for something that in OChem we call multi-step synthesis, which, like mechanisms, is something that you will not be able to get away from. So it's very important to start mastering this while it's easy. So it's a little bit less difficult when we start throwing on more reactions and more functional groups.